So I wanted to ask myself the following question. Consider this blue family of Poncelet triangles ABC, inscribed in an ellipse and interscribing some elliptic caustic, the brown thing. Okay? Now the question I wanted to ask myself was, what should the shape of this caustic be if I simply specified its center, O, and the fact that over the family, um, the barycenter should remain stationary. What should the shape of this caustic be, right? So as you can tell here, if I move the center, the caustic is changing shape, right? Now, for some technical reason, O cannot go beyond this dashed gray ellipse here. But if I can flex, if I flexibly move O around, I can find the shape of the caustic that over the family is going to keep the barycenter x2 of the family stationary. And by the way, x2 is always going to lie on the line that connects the center of the system to the specified center. Okay, so how am I doing this? How can you achieve that? Basically, you realize that this must always be the affine image of the MacBeath family shown here on the left. Why the MacBeath family? Because the MacBeath family has the property that it conserves or it keeps its barycenter also stationary. In the case of the MacBeath, the barycenter will be stationary on the major axis of the caustic. Now, what's the MacBeath caustic look like? It basically has one of its foci on the, so the MacBeath family is circumscribed and it has one focus of the caustic on the stationary circumcenter or the origin, and the other one at the stationary orthocenter. Now, you know that affine transformations preserve centers of conics. So the center of a conic is equi-invariant with respect to affine transformations, and that the barycenter is the only triangle center that is equi-invariant with respect to affines. Okay, so I can translate this question that I'm asking, what should be the caustic, okay, in this right hand side family here that keeps x2 stationary, by saying what's the MacBeath family, okay, whose caustic center, O prime, is the affine image of my specified O. Okay, so what is the affine transformation that sends this outer ellipse to a circle? It's implicitly being computed here, and it's a trivial one. All you need to do is contract the x-axis by b over a, right? So then the outer guy gets sent to the circle. Now, when you do that, you want the caustic, the unique MacBeath caustic, whose foci lie on the center of the circumcircle and on the reflection of that center about the affine image of O. So O has an affine image. We just said that centers of conics are equi-invariant. So when you do this, this other focus here is basically the reflection of the center about this affine image O prime, and then you get a unique caustic here using a Blaschke procedure that gives you the eccentricity of this thing with foci on these 2 points, and then you get a Blaschke or a Blaschke caustic for a MacBeath system, okay, whose caustic is centered on the affine image of the specified O. Now we know that MacBeath conserves or keeps x2, its barycenter, stationary on the major axis. So since the barycenter is equi-invariant with respect to affine transformations, it's also going to be stationary on the pre-image here. Okay. Now notice that x2 is going to be collinear with the center of the outer ellipse and my specified O, because affine transformations preserve collinearity, but affine transformations do not preserve foci. Foci of my conic is not equi-invariant. So you can see here that while on the MacBeath x2 lies on the major axis of the caustic, it does not lie anymore on the major axis of my target system. But what's cool about this is that I can now sort of visualize what's happening to the caustic for systems that preserve the barycenter. This is sort of was inspired on a previous calculation where we found the circle, and it would be more or less this guy here, that keeps So the circular caustic that keeps the barycenter stationary, right? So you can see that the pre-image is not a circle at all. The caustic is this upright ellipse, okay? And you can see here that the foci are almost close to each other, so that's almost a circle, but that gives you an idea of the family of caustics for specified O that keep the barycenter constant, and when that's done, the barycenter is going to lie on the line that connects the center of the system and O. Okay, that's all I have. See you on the next video.